techniques for solving further maths and differential equations. In part 2, what we're going to look at is modelling with differential equations, real world type situations which can be modelled by a differential equation, which you may have to formulate and or you may have to solve. There's some basic things that we're going to need to know for background for what we're going to do today, folks. So first of all, we'll often have questions involving rates of change. So you should remember that some quantity y, which is changing with time, its rate of change is dy by dt. And a few elementary ideas from A-level mechanics may be required. So I'm going to use x to denote the displacement of some object, v to denote its velocity, and a its acceleration. Velocity is the rate of change of time, so velocity is dx by dt. Acceleration is the rate of change of velocity, so acceleration is dv by dt. And those, combining them together, means the acceleration is d2v by dt squared. The only other thing you might need is the fact that Newton's second law, the resultant force acting on an object is equal to the mass times acceleration. Now, in this lesson, I'm only going to look at first order differential equations. Any first order differential equations which arise can either be solved by separating the variables, which really means it's an A-level maths question, or by using an integrating factor. These are what's most likely to arise on a further maths question. Okay, folks, here is example 1. So example 1 says a particle of mass 2 kilograms starts from rest at the origin. So starting from rest at the origin means when t is 0, if it's at rest, its velocity is 0. And if it's at the origin, its displacement x is also equal to 0. After t seconds, the force acting on it is 12 times t plus 2 to the minus 2 newtons. I want to find expressions for its velocity v and its displacement x in terms of t. So a very simple diagram to illustrate what's going on here. I've got a force F, which is 12 t plus 2 to the minus 2. By Newton's second law, F equals ma. We get the following equations, that 12 times t plus 2 to the minus 2 is equal to the mass, which is 2 times the acceleration. Now I can turn this into a differential equation linking v and t, which I can then solve to get the velocity. I'm going to divide both sides by 2, and I will get 6 times t plus 2 to the minus 2 is equal to dv by dt. So there you go, there's my differential equation connecting velocity and time. And actually, this can be solved by separating the variables. Therefore, this could actually really be an A-level maths question rather than a further maths questions. So if you times across by dt and integrate both sides, you'll get the integral of 6 times t plus 2 to the minus 2 dt is the integral of dv. If you integrate the left-hand side, it's a linear function. The power is not minus 1, so you can increase the power and divide. You will get minus 6 t plus 2 in brackets to the minus 1. The integral of v is just v, and you need to put a plus c on one side or the other. Because I know that when t is 0, v is 0, because it starts from rest. If you sub that in, you will get 6 times 2 to the minus 1 is minus 3 is equal to c. So therefore, we get minus 6 times t plus 2 to the minus 1 is v minus 3. So therefore, my expression for v is, if you add on 3 to both sides, 3 minus 6 times t plus 2 to the minus 1. There's the first part of that done. It also wants an expression for the displacement from the origin in terms of t. Well, I can get that by going to this thing I've just proved and now replacing the velocity with dx by dt. So this means that dx by dt is equal to 3 minus 6 times t plus 2 to the minus 1. This again is a separable variable differential equation. You can times through by dt and integrate both sides. So I'm going to get the integral of dx is the integral of 3 minus 6 times t plus 2 to the minus 1, dt. The left-hand side integrates to give x, 3 integrates to give 3t. 6 times t plus 2 to the minus 1 is 6 over t plus 2, so that gives a log, so I get minus 6 ln of, there should be a modulus sign, but I'm just going to use a bracket, ln t plus 2, and you need to put a t on both sides. I'll put a c on this side. So we know that when t is 0, x is 0, so 0 is equal to 3t is 0 minus 6 ln 2 plus c. So c is 6 ln 2. So the expression for its displacement is 3t minus 6 ln of t plus 2 in brackets, add 6 ln 2. That's the displacement of the object. Now, I said at the beginning, that's really an A-level maths question because you could separate the variables. Example 2 is a bit more like the kind of thing you might be required to do in further mathematics. So a particle P is moving in a straight line under a variable force, which gives rise to an acceleration given by that at time t. So the acceleration is the time plus 3 times the velocity of the time. V is the velocity, t is time. Find an expression for v in terms of t, given that p is instantaneously at rest when t is 2. So when t is 2, the velocity is 0. So what I'm going to do is, first of all, turn this into a differential equation, and then we'll think about how to go solving this. So the acceleration is the rate of change of velocity. So this means that dv by dt is equal to t plus vv over t. There's my differential equation linking v and t. Now, students, this one cannot be solved by separating the variables, which means the integrating factor is needed. So just to remind you of the integrating factor applies if you have a differential equation of the form dy by dx plus p of xy is equal to q of x. You multiply through by the integrating factor, which is e to the integral of p of x. And I'm going to use this method in a minute, but different letters are required. Instead of v, instead of y, we now have v. Instead of x, we now have t. So I need to rearrange this slightly into dv by dt minus 3 over t lots of v equals t. And now I can apply the integrating factor method. So instead of p of x, we have p of t, and p of t is minus 3 over t. So my integrating factor for this is going to be e to the integral of minus 3 over t dt. Okay, so by some straightforward different integration, that integrates to give e to the minus 3 ln t. Don't worry about any modulus signs. Don't put a plus c when you integrate that. If you take the minus 3 in as a power, that equals e to the ln of t to the minus 3, which is just t to the minus 3. Let me now get rid of that bit. So what we now do is multiply this differential equation here by the integrating factor, which is t to the minus 3. And if you do that, you will get t to the minus 3 times dv by dt minus 3 times t to the minus 3 divided by 3. So take 1 off the power, gives me 3t to the minus 4v is equal to t times t to the minus 3 is t to the minus 2. Now, the integrating factor method is always such that the thing on the left-hand side is the derivative, in this case with respect to t, of the integrating factor, t to the minus 3, times the other letter, which in this case is v. So this becomes d by dt of t to the minus 3v equals, it's still t to the minus 2 on the other side. Integrate both sides and you'll get t to the minus 3t is the integral of t to the minus 2 dt. And that's okay. Increase the power by 1, t to the minus 1, divide by the new power. So that's minus t to the minus 1 plus c. A c is needed at this stage. Now, what I'm going to do before I work out c is I'm just going to make v the subject. T to the minus 3 is 1 over t cubed. If you multiply everything through by t cubed, you will get v is minus t to the minus 1 times t cubed is t squared plus c t cubed. Now, because we know it was instantaneously at rest when t is 2, we know that when t is 2, v is equal to 0. So this means that 0 is minus t2 squared is minus 4 plus c times 2 cubed, which is 8c. So it turns out that c is equal to 1/2. So therefore the expression for the velocity is v equals minus t squared plus c, which is 1/2 t cubed. That's the expression for the velocity of the object. Okay, folks. So the example I'm going to do next, I shall warn you, is a little bit tricky. Our exam board does quite like questions of this type. It's a certain type of situation which can be modelled by a differential equation which we can solve by using further maths material. So we are given the following information. I'll try to draw a picture to illustrate what's going on. This is not straightforward, but I should warn you, our exam board do like this kind of question a bit. So we've got the following. A storage tank initially contains 1,000 litres of pure water. Liquid is removed from the tank at a constant rate, 30 litres per hour. So here's my tank. I've got liquid going in at 30 litres per hour and a chemical, garbage. Liquid is removed at 30 litres per hour. Let's change that. So I've got liquid coming out at a rate of 30 litres per hour. And I've also got a chemical solution added in at a rate of 40 litres per hour. If you think about that, that means the volume of water is going to increase. The chemical solution which is added contains 4 grams of copper sulfate per litre. And we are told the following. X is the number of grams of copper sulfate in the tank after T hours. We're going to assume that the copper sulfate dissolves instantly and immediately disperses throughout the tank. I've got to show that this situation can be modelled by this differential equation here. dx by dt is 160 minus 3x times over 100 plus t. Now, students, this is not something you're going to write down instantly. In an exam, this differential equation, deducing this, is worth 4 or 5 marks. So the first thing to notice is this. Not only is the amount of copper sulfate X in the tank going to change, but the volume of liquid in the tank is going to change as well. And the volume is going to be relevant. So I'm going to let V equal the volume of water in the tank. Now, I can say I can write down quite easily a formula for V, because every hour 40 litres of liquid goes in and 30 litres of liquid comes out. The rate of change of volume, dV by dt, is 10, because 40 is going in and 30 is coming out. So this means V is going to increase linearly. V is going to be 10t plus something. But initially, we know there are 1,000 litres of pure water. So we can write down that the volume is equal to 10T plus 1,000. Okay, folks, you can't do this question without taking into account the fact that the volume changes. Then, how can I come to the fact that this thing here? So what about dx by dt? So the reason that the amount of copper sulfate is changing is it's increasing because of the water flowing in, but it's decreasing because some water flowing out will contain copper sulfate in it. So what I can say is the net result is that dx by dt, the rate of change of x, is equal to rate in minus rate out. And that's going to lead to these two terms here. Now, the rate in is quite straightforward because chemical solution is added to the tank at a rate of 40 litres per hour, and each of those litres contains 4 grams of copper sulfate. So I can say straight away that the rate in is going to be 40 times 4, which is 160. So that's where that 160 comes from. The rate out is a little bit more complicated because the liquid flowing out will contain some copper sulfate in it, but the amount of copper sulfate is going to change as the process continues. I'm going to use an argument based on concentration. So I claim the following is true. The concentration of copper sulfate, I know that's not the proper chemical symbol for it, CuSO4, I think, folks. The concentration of copper sulfate is X over V, the amount of copper sulfate divided by the volume. But that will be the same as the rate out divided by 30, because every hour 30 litres of liquid flows out. If the concentration in that liquid is the same as the overall concentration, the rate out divided by 30 is X over V. So what that means is that the rate out is going to equal 30X divided by V. But wait a second, earlier we said that V is 10T plus 1,000. So that's going to be the same as 30X over 10T plus 1,000. And I can divide top and bottom of this by 10 and maybe switch the terms on the bottom. So that's just the same as 3X divided by 100 plus T. So combining those together, dx by dt will be equal to 160, that's the rate in, minus the rate out, which is 3x divided by 100 plus t, and we are done. So this is not straightforward, folks. You've got a complicated situation. You've got to work out the rate at which the copper sulfate is going in. That's constant. The rate at which it's flowing out varies. You need to take into account that the volume of the liquid will changing. That's part A. And I'm positive in a question of this type, part A is going to be a show that question. Okay, so I'm just going to rub that out and then I'll have a go at part B of this. Please pause the video if you need a bit more time to write all that stuff up. Okay. So part B says, hence find the number of grams of copper sulfate in the tank after 6 hours. So this is the same as saying when T is 6, what is X? Sorry, what about X is 6? What is X? To do that, you would need to find an equation linking X and T. And this differential equation, if we solve it, will give an equation linking X and T. Now, again, folks, this is an integrating factor differential equation. The standard form is dy by dx plus p of x times y equals q of x. The integrating factor is e to the integral of p of x. In our case, instead of y, we now have x, and instead of x, we now have t. So I want to write this as dx by dt plus a function of t times x. So if I add the 3x over 100 plus t across, we get 3x over 100 plus t equals, we still have 150 on the other side. So the integrating factor for this will be e to the integral of whatever x is being multiplied by 3 over 100 plus t dt. And that's okay. That's 3 over a linear function. So you get an ln, you get e to the 3 ln of 100 plus t. You can bring the t in as a power, 3 as a power, sorry. So e to the ln of 100 plus t cubed, which is therefore 100 plus t cubed. I am now going to multiply the entire differential equation by the integrating factor of 100 plus t cubed. So when you do that, you will get 100 plus t cubed times, dx by dt, plus, if you times the second term, 100 plus t on the bottom cancels out one of the 100 plus t's in the cubed one. So you get 3 100 plus t squared x equals, on the other side, we get 160 times 100 plus t cubed. The left-hand side will always be the derivative of, in this case with respect to t, because it's functions of t, the integrating factor 100 plus t cubed times the other letter, which is x, equals the right-hand side is still 160 into 100 plus t cubed. You can then integrate both sides to get rid of the differential. So you get 100 plus t cubed times x is the integral of 160 into 100 plus t cubed, which is, it's a linear function to the power of something, increase the power, so it's 4, divide by the new power and the differential of the bracket, which is 1. So that should integrate to give 160 over 4, which is 40 times 100 plus t cubed. And you must remember to put a constant at this point. So there you go, folks. This is my general solution to my differential equation. Now, there should be enough information in the question to work out C. And this is what we can do. Think about what happened initially. So X is the amount of copper sulfate in the tank. Initially, it's got pure water. So when T is 0, X is 0 because there is no copper sulfate in the tank. I can sub that into this to work out what C is going to be. So if you plonk in T is 0 and X is 0, the left is something times 0, which is 0. The right is going to be some very big number, 40 times 100 cubed, which is 4 times 10 to the 9, written in standard form plus C. So therefore, C is minus 4 times 10 to the 9. So if you sub that in, and you might as well make X the subject as well, here is the solution. X is 40 into 100 plus t cubed plus C, which is minus 4 times 10 to the 9, all over 100 plus t cubed. That is the amount of copper sulfate when t is at time t. The point of part B was to find out what X is when t is equal to 6. So you'll get x is 40 times 100 plus 6 is 106 cubed, minus 4 times 10 to the 9 divided by 100 plus 6 is 106 cubed. And if you type that into your calculator very carefully, you should get 882 grams. Units may well be required to 3 significant figures. Those are the number of grams of copper sulfate in the tank. Now, these kind of questions are very likely to end with a kind of modeling bit. Explain how the model could be refined. And there is kind of a standard answer that they are looking for in this question. Okay, so in this question, we assumed that the copper sulfate immediately disperses through the tank on entry. And that leads to the fact that the concentration of copper sulfate in the entire tank is the same as the concentration in the liquid which is flowing out. That's unlikely to be true. There's likely to be more copper sulfate at the bit of the tank where the liquid is coming in. So if I wanted to refine the model, I would change that assumption. Now, it would make the differential equation much harder, but I'm just going to say something along the lines of this, that I will assume that the copper sulfate does not immediately disperse. On entry. So there you go, folks. There is my refinement, but that would make life so much harder to solve. Now, lovely students, here's what I'd like you to do. Can you please now press pause, and then can you have a go at the now you try question on the next page? This will take you 5 or 10 or 15 or 20 minutes to do. It's very similar to this one. It's a slightly different context. I will then go through the answer to that question. So pause the video, have a go at the question on the next page, then check your answer. Okay, students, so answer is the following. So first of all, the volume of liquid in the tank is required. So that's V. So because 30 goes out, 40 goes in, it goes up by 10. So it's 10T plus something. It's 10T plus 400 because that's the initial volume. The rate of change of x dx by dt is rate in minus rate out. The rate in is 10% of 40, which is 4 liters per minute. The rate out requires a concentration argument. The concentration is x over v. So therefore, the rate out divided by 30 is x over v. So the rate out is 30x over 400 plus 10, which gives you 3x over 40 plus t. So consequently, dx by dt is 4 minus 3x over 40 plus t. Then, to solve this differential equation, rearrange it to use the integrating factor method. The x by dt plus 3x over 40 plus t is 4. The integrating factor is e to the integral of 40 over t dt, which simplifies, to give 40 plus t cubed. If you multiply through by that, you get this, 40 plus t cubed dx dt plus 3 times 40 plus t squared is 4 into 40 plus t cubed. The left-hand side is the differential of 40 plus t cubed times x. So therefore, 40 plus t cubed x is the integral of 4 into 40 plus t cubed, which simplifies to just give 40 plus t to the 4 plus c. Initially, we are told there's no acid. So in T is naught, X is naught. So if you plug that in, you get C is minus 2,560,000 or 2.56 times 10 to the 6. Here is your expression for X. If you sub in T is 7, you should get a value which rounds off to give 22.3 milliliters. Again, the standard assumption at the end, we assume the acid does not immediately disperse on entry. Okay, students, you are now in a position where you can do the next exercise, which is exercise 1.